in the, I think people say it's the D-Glab equation. I think D stands for Dockschitzer, L I can never remember, A is Autorelli, and P is Parisi. So L, if you know what L is, tell us. So the modified Pathan distribution functions should also satisfy the D-Glab equation. Okay? And if we modify it wisely, this piece will be cancelled by this piece, and we remove the collinear divergence. And we can see that we introduce some corrections such that we can have linear order contribution and extra contributions from alpha s from 1 over lambda, that is the log mh over mb part. We add everything together, we get this next to leading order contribution, and with a k factor of about 1.5. And let me emphasize again, this is very important if we have type 2 Yukawa interactions with a large tangent beta. I oversimplify this, but I want to give you some flavor that QCD corrections can be important if we want to precisely determine the cross-section of a process we are looking for. Now let's focus on these two channels that we have discovered this scalar particle. So we have protons with gluons generating a Higgs through loops, a top or a bottom. MT is 173 and MH is 126. If MH is less than 2MT, then there is a trick we can do. We don't have to go through this messy calculations. So this is the commonly used loop integral that we have. A may go from 1 to a large number, and usually we deal with about to 5. If A is 1, we call a tadpole. If A is 2, some people may say it's like a setting sun because you have a 2-point function. If A is 3, you have a triangle I just showed you. If A is 4, you have a box. If A is 5, make a guess what that is. You have a pentagon. Okay? Tini Weltman showed us a nice trick. You don't have to do this time-consuming and not very rewarding calculation all the time. You can do large mass expansion to find a quick answer.
What do you mean not time-consuming?
Time-consuming
formula. It's simpler than the lower one.
Oh, no. This is simplified from propagators that we have to introduce, Feynman parameters, introduce many other things. So this is the oversimplified version. Actually, eventually, this will be much simpler because if you take the leading order, these are negligible. What I was trying to say is this is much easier than this. If you have only independent loop momentum plus a large mass term, if you don't have to worry about this term, life is nice and simple.
I don't know what you mean. See, this is an integration from infinity, minus infinity to infinity.
Correct.
You just write the first term in terms of complete square, and the plus minus something become constant. That's what you will get at the end.
Okay, I should have typed it clearly. So originally we have 1 over, suppose we have the triangle. So we have D1, D2, D3. D1 is L squared plus M squared. D2 is L plus P1 squared plus M squared. D2 is L plus P1 plus P2 squared plus M squared. It was quite hard if we have to do all the combinations. Actually, triangle is not that hard, but for a box, it can be time-consuming and a lot of algebra to do. But if you follow Weltman's trick, then you can do a quick calculation. Suppose you can neglect higher order terms. If you can group only this term, you can write a messy expression to be L squared plus M squared to the 4th. And then you can find the answer right away. Okay? The next line will be the decoupling theorem if mass is large. So in 75, Appelquist and Carozon, they suggested If you have particles, they will disappear in your calculations if they are very, very massive. But there is one exception. And that exception is if you have heavy fermions and spin zero states, then they don't decouple. You are going to find a finite contribution. I think we learned this from Pathan's talk of when you have Higgs, when you have extra degrees of freedom in the loop. So if we follow that trick, then we are going to say glue to Higgs doesn't have to go through a triangle. You can just say take the large mass limit, follow Welterman's trick, and you have a simple term with CH. CH is alpha s over 3 pi. Okay? And let's appreciate the simpleness of this expression compared to this equation. So we have an amplitude that is rho times 2 plus 4 rho minus 1 times I. I is from what Welterman and Passerino will call C naught. It has 3 denominators. We have to combine with 2 Feynman parameters, then combine with dimensional tricks to get this formula. So if we take the large mass limit, then this F becomes a simple formula, and we have a simple expression that gives us 1 over 3 from these messy expressions. And this fortunately has a closed form. But if we have a box, this doesn't have a closed form. We have to write it in terms of what people call the diagonal logarithm or called the Spence functions. And you can only do Taylor expansion, no exact solutions. Okay? And now it's time for some fun. One time in a conference, Howard Georgi said, many people like to do loop calculations. But to me, most loop integrals are unnecessarily complicated. So he suggested if we have talented and skillful experimentalists, we can write down effective Lagrangian that we like. Then we tell our friends, here are some masses and couplings. Please measure for us. Then we can use that Lagrangian to do our calculations. Of course, effective Lagrangian has its limits. Okay? And what are the guidelines we should follow to write down effective Lagrangians? Weinberg repeat this over and over again, that we should write effective Lagrangians with Lorentz invariance, cluster decomposition, and unitarity. Most of the time we need unitarity, but for vector boson scattering, unitarity may become a funny concept, because if you have WL at high energy, your cross-section will not satisfy unitarity. So Georgi suggested we follow Weinberg's guideline for effective Lagrangian, and we should study physics without being confined by what most people look for, renormalizable or fundamental theory. And this is for fun if you have read the New Testament, and it's fun to mention some scripture in the physics talk, but these are quotes from Georgi. Okay, the original statement in the Bible, what therefore God has joined together, let not man put asunder. This is talking about a husband and a wife. But Georgi said, what therefore God has put asunder, joined to, sorry, I should get rid of this. Let not man join together. Because many people were looking for a theory of everything, looking for unification. But Georgi suggested in the next statement, let's try to let the day's own trouble be sufficient for the day. We can go several steps ahead of us and without knowing whether it's correct or not. Let's do one step at a time. So sometimes I find his book fascinating. I also find some of his statements fascinating. So ignore these first 2 words. What he was trying to say is the 3 couplings God has put asunder. Let not man join together. He suggested we should do something practical and useful. Yes, you have a comment?
Joking. saying
Yes.
that he was not a deacon for nothing. However, what about Glashaw's comment on Georgia's comment? I think he's an atheist.
Okay, another different opinion about effective Lagrangian I also found fascinating. Peter Lepage used to ask students, give me a reason why QED works so well. Give me a reason why Fermi theory worked so well for a while. For different reasons. QED works so well because ME is very small. And we have to wait until MW to show us QED has a brother that is how many times more massive? 80 GeV, 80 times 10 to the 80 times 10 to the third power over 0.5. Okay, his brother is big and heavy, and electron is so small. So QED is so successful. Lepage suggested, I think this is the probably the, let me say, the Weltman doctrine. Weltman likes to calculate everything as precise as possible. If you have some effect that can come from a loop of fundamental theory, Weltman will try all his best to tell you the answer. He wrote a code called form factor, and it was written in the machine language of a computer called CDC. I think we probably, Xiaogang and George and myself probably have used CDC, and most of you probably don't know what CDC is. It's a mainframe computer. It's quite hard to use. However, it's quite powerful during that time. And Weltman wrote machine language to calculate loop integrals for EE to mu. He wants to demonstrate that Weinberg model has some clues even before W and Z have been discovered. Okay, so Weltman kept some constants up to 120 digits. I hope you find this impressive. So I think Lepage may have been influenced by those thoughts. So Lepage suggests most relevant effective Lagrangians should be consequences from fundamental and renormalizable theories. I'm going to show you, actually I showed you already. Okay, so if we follow Lepage's concept, we have this time-consuming heavy-duty calculation. After a while, we know that MT is much greater than MH, so we can have an effective Lagrangian. It can be expressed in a simple form.
Excuse me, actually, MT is not much greater than MH, so why does it work so well?
That's interesting.
Why is MT already closed, I mean, for the triangle graph?
Okay.
You know, I think most of us just remember a formula, so it works, but...
if we do the, let me see. Oh, I think here's the reason. Right here. Because if we do expansion, let's say, actually, so we get a factor of 10 from the next order, and we also get 173 over 126 square. So it's 10 times 173 over 126 square. So it's about, actually not, let's say 1.5, so 15, a factor of 15. And then we square it. So actually that's not right, because there's also interferences. So a quick answer is I don't quite know. But the only thing I know is the next leading order will be about 1 over a factor of 15 times smaller.
So it's really the coefficient.
Okay, so if you are We don't have a German, so let me try to tease the Germans. Okay. I guess the German physicists, they like to do loop calculations. They like to do
power
2 loop. They like to do 3 loop. So I guess they follow the Veltman-Lepage concept. We should do as precise calculations as possible. However, I think I want to tell postdocs and students a wonderful idea that Lepage mentioned. He likes to say polyvila regularization has more physical meaning than dimensional regularization. If you know the cutoff, it's very possible you are going to find new physics soon. So if you know the cutoff for QED, whenever QED breaks down, then you know something exciting might come. So if you behave like Germans, like to do loop calculations, and when you find your loop calculations break down, do not feel upset. Maybe you should feel happy if you follow polyvila regularization. That may mean something important could happen soon. Okay, now let's come back to trilinear Higgs couplings. CMS used kappa F, so we suggest, we means Dwayne Backus and myself, we introduce a kappa T for the TTH coupling. Most of the time we take kappa T to be 1, and later we may change it, but let's set it to be 1. We also do triple Higgs interaction with a kappa compared to the standard model. And if kappa is positive, you can see that the box doesn't care about trilinear coupling. The triangle depends on kappa. The total is decreased as kappa is increased. So this is destructive interference. If you write it in the quantum mechanical form, there is an interference parameter we call alpha. This alpha is about -0.8. So this is not exactly 1. If it is 1, then it will be complete destructive interference. It's 0.8, it's quite close. Now, how can we enhance this cross-section? Which, for theorists, we just change the sign. But we have to figure out why. Is there a model? Is there a reason this kappa may change sign? So we can consider both cases, but for kappa positive, it's more conventional or canonical if we follow the standard model. So now let's consider uncertainties. This is the standard model calculation for cross-section with kappa. And if we say we have a 20% uncertainty, or if we have a 40% uncertainty, then this is a large area that the cross-section can cover. So for 100 TeV, we can determine the cross-sections more precisely. Okay. So the uncertainty is not as drastic. So let me try to finish in 8 minutes. And this is borrowed from Wisconsin group that I mentioned. They studied HH decays into BB bar and gamma gamma. And they study 2 ways: apply multivariable calculations, analysis, or apply conventional cut analysis. They found out that conventional cut analysis is not as good. So the improvement seems to be quite striking. Okay? And this number is the kappa H that I mentioned. So this is for 8 TeV, and they found out this kappa can be as large as 7.5. That means at 8 TeV, we probably don't know anything, because lambda triple H over lambda triple H in the standard model is almost a factor of 7. Yes.
How can they be so confident for 3,000 in the standard model? They assume the same background or what?
That I don't know.
Well,
Probably.
I guess so. Otherwise,
I guess so.
I guess
So it's standard trick.
yes, they need to scale up things.
Experimentalists have to face it.
Yeah.
Okay, and now they suggest at 14 TeV, if we have enough luminosity, light can be much better. It will go from a factor of 7 to a factor of about 0.4. If we have enough signal events, and if the background doesn't, if the reducible or unphysical background do not mess up their analysis. Okay? So now let me draw some conclusions, and I should mention that at lunch, George told me that Nimura and the collaborators also did a study for trilinear coupling and Higgs pair productions. And my conclusions basically borrowed from Werner's paper. And they found out, they compared BB gamma gamma to BB tau tau. And BB gamma gamma is much better than BB tau tau. BB tau tau will be overwhelmed. And there is some minimum that we could see in the cross section when the triangle has destructive interference with the box diagram, and therefore you have a minimum at some point. And that kappa is about 2.5. And also, this is the region that we are going to see some amplitude that almost vanishes if kappa is between 1.1 and 2.45. This is in MHH distribution. And if we have 8 TeV only, then kappa can be as large as 7.5. Whatever we have measured, actually we don't know. It has a large uncertainty, we don't know. But with with almost twice the energy, with enormous luminosity, assuming pile up will not kill the signal, and also unphysical background will not kill the signal, then maybe we will be able to determine lambda with a 40% uncertainty. Thank you.
Pretty depressive. Depressing. Okay, no, that's the question. Oh no, okay, I thought I saw. So by 2030, we reach 40% measurement of HH with a bigger frame.
Right.
Okay, we need linear collider.
In that sense, we do.
Yeah. If LHC can only reach this.
How well can linear collider do?
I don't know, but the RBSD will be better than this, right?
Mm-hmm.
Oh, what about this 100 TeV collider?
100 TeV. Good thinking. Good thinking.
So
Yes.
it was not in the larger et al. paper?
They did not show.
Oops.
Let me see. Maybe wake it up. No.
You had some cross section on 100 TeVs.
I think for a naive cross section without decay, I think the decay will mess up things. Okay. If we just study the Higgs cross section, I think the uncertainty is about 15%. However, when we consider Higgs decay into BB bar and gamma gamma, fill in the mass resolution and background, let's say, I'm just making a wild guess, I would say at 100 TeV, the uncertainty may be between 20% and 30%.
But in a certain sense, the 100 TeV machine happens, quote unquote, after linear collider.
Yeah.
So yeah, one can compare, but I say it's depressing because it's 2030. I don't think the linear collider is maybe running, but that's the time scale. The 100 TeV is, I don't know, what's the time? But it's a good question to say, since we saw a much larger cross section, it's irrelevant.
Right.
Yeah. So the neuroscience is actually there. What was your conclusion?
Yes, tell us.
About trilinear coupling.
Maybe let me give you the microphone. Then we can all hear better.
Well, it's just for comparison. Since
Yes. How, from your study or from your personal insight, how well can we measure this trilinear coupling?
I think my point is LHC is difficult, and so my perspective is better than ILC.
Okay, how well can ILC do?